Let's try it again. All right, I'm being very intentional about this. So I'm going to make the first hill very, very high. And then I want to make the first loop not as high as the first hill. And then I want to make the next hill higher than the first loop, but not as high as the first hill. Okay? And then back down to the ground. This is the roller coaster. And I want to add in some measurement values here. Okay? So within my measurement values, I want to, first of all, provide for myself a baseline. So on my baseline, I'm going to say that the ground level is just below this lowest tip here. And it's right where you finish the roller coaster. Now, you know that on a roller coaster, the next step would be that part where there's some chain pulling action that pulls you chug, 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 up to the top of the hill. And that's where you get released over on this end. So it's really a closed loop. So I'm giving up the chug, 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 chug part where the tow line pulls you up to the top of the hill. I'm not going to draw that part of the roller coaster. I just want to do the coasting part of the coaster. Okay? The true coasting part. So if I start out in this roller coaster up at this height initially, and I want to give myself a height of 20 meters. And at this point here, I want to give myself a height of 3 meters. Let's make it 3.00 meters. At this height here, I'm going to be a total of 13 meters at the top of the loop. And at this height here, I want to be a total of 15 meters. Okay, so my scale's not perfect.
What's the
3.00.
What is that for, though?
Just the height at this point right
Okay.
here. 3.00 at that little low spot. And of course, at this point here, it's got a height of 0 meters. Now I'm going to go through and I want to label up the different positions. I want to call this position A. I want to call this position B. This is position C. This is position D. And this is position E. So 5 positions that are what I would consider to be critical positions on this particular roller coaster. I want to give my roller coaster itself a mass. So I'd like to say that this is a roller coaster with a mass of 500.0 kilograms. And I'm going to give it an initial velocity. So it doesn't start from rest. It starts with a velocity of 0.500 meters per second. Yeah. The mass is 500 kilograms. And the initial velocity, or the initial speed rather, is 0.5 meters per second. So just getting up over that edge. It's going to be a multi-part problem. And just like when we were dealing with projectiles launched vertically, the first thing you often want to do if you're given enough information is, well, here's part A, find the total mechanical energy for the roller coaster car. Find the total mechanical energy for this coaster car. And we said previously the total mechanical energy in this context is just going to be made up of kinetic energy and gravitational potential energy. So E total is equal to EK plus EG. Now there's only one point so far on this roller coaster where we know enough information to figure out what E total is. Where is it?
Point A.
Yeah, point A. So we could say E total is equal to EK at position A plus EG at position A. You notice I'm using the subscripts to specify which position we're talking about.
But don't we know position E?
We do know position E, but we don't know the velocity at position E. So we can't do kinetic energy at position E. We do know enough information to know kinetic energy at position A and gravitational potential energy at position A. So that's why we choose that one to focus on to start with. Yeah?
So the EG, is it if it goes down the like roller coaster?
No, it actually possesses the gravitational potential energy at that height. Yeah. All right, so let's plug in some values. Actually, let's set up our formula first. EK is 1/2 m velocity at position A squared plus EG, which is mass times acceleration due to gravity, times, now, you want to just drop this delta dy stuff and say height? It's one letter. Height at position A. Because we know that's the same thing as delta dy, displacement from the origin in the vertical direction. Now let's start plugging in some values. E total is equal to 1/2, we said the mass is known, 500 kilograms, times the velocity, 0.5 meters per second squared. I'm dropping off those extra zeros just to save space so I don't run out. Plus 500 kilograms times 9.81 meters per second squared times a height of 20 meters. I still almost ran out of space. So again, let's calculate the kinetic energy separately from the gravitational potential energy, because you never know. Sometimes somebody later on will say, how much kinetic energy did it have to start with, or something like that. So don't let somebody throw you a curveball. You might as well calculate them separately and add them up. 0.5 squared times 500 times 0.5. What do we get? Some of you are trying to do it in your heads. 62.5? Sounds about right. 62.5 joules plus 500 times 9.81 times 20. Yep.
98,100.
98,100? Oh my gosh. 98,100. Holy moly. Most of this energy is wrapped up in gravitational potential energy. Would you believe it?
Yeah.
That's crazy. This thing is a big thing up high. All right. This thing's going to go freaking fast when it gets to the bottom, eh? How'd you like to be on that roller coaster? All right, so the total mechanical energy, 98,162.5 joules. That's the total mechanical energy. Just adding those two values up. Can I take this away now? I won't take the picture away, but I want to take this away. We found the total mechanical energy. And what I'm going to do is I'm going to fold over what we just wrote and keep the picture so that we don't lose that. I know you have it on your page, but I don't have it on the screen unless I just do this. Okay? Oh, it's got an autocorrect function. Don't worry. It'll be back again. Ooh. Ooh. Okay? Ooh. All right, so we got our picture here. Part B. Part B. Really quick one. What is the total mechanical energy at each of the other points? So I could say E total at position B, E total at position C, E total at position D, and E total at position E. What's the value of that at each of the other 4 points?
The same?
Yeah, the same. It doesn't change. Why would it? If we're neglecting friction, in this case we're neglecting friction because friction would rob energy from this system. This is a closed system that doesn't lose any energy to its environment. So we're neglecting friction and air drag. A big oversimplification. I know that you know that. But these guys are all going to be equal to the value that we just calculated, which was 98,162 joules. All the same. So that part B is a nice easy one. I'm going to set it off to the side for a minute. I want to find, for part C, for part C, find the gravitational potential energy at position C. I want to know how fast I'm going at the top of that loop. So first, I have to know the gravitational potential energy there. At point C. So part C, find the gravitational potential energy at point C. So I could say EG at point C is equal to mass times acceleration due to gravity times the height at point C. I'll use height instead of delta dy. Same thing. Is equal to 500 kilograms times 9.81 meters per second squared times 13 meters.
Is it maintaining the same, the same velocity?
Well, what do you think? If it's losing gravitational potential energy, is it going to gain something else? Well, gain kinetic energy, right? So look, we'll get to it. Yeah, it might pick up some speed. It might lose some speed by the time it gets to the top of the curve. Okay. Yeah, we're neglecting friction now, so that's a big neglect. All right, so 500 times 9.81 times 13. What do you get, Angus?
63,765.
63,765 joules of energy. That's just wrapped up in gravitational potential energy. So a part D might be find the kinetic energy. At point C. How could you find the kinetic energy at point C? Yeah.
Minus the gravitational potential energy from the
Huh. Yeah, take the gravitational potential energy away from the total energy, and whatever's left over has to be the kinetic energy. So you might say, all right, well, E total is equal to EG plus EK. And so if I want to know how much EK is, I'm going to say E total minus EG is equal to EK. And since I have values for EG and E total at this point, I can say EK is equal to, and I'll just plug in my values, E total, which is, what was E total again? 98,162. Yeah, 98,162 joules minus 63,765 joules. How many joules do I have wrapped up in kinetic energy? Yes, sir.
34,397.5.
34,000?
397.5.
Beautiful. Joules. Oh, because we forgot a 0.5 right here? Okay. Alrighty. So that's how much kinetic energy we have. Now, if we know how much kinetic energy we have, can you imagine that we can find out how fast we're going? All right. Let's do it. Let's just set it up. So if we're going to do a part E, we could say how fast is the coaster at point C. And in that case, we could just say, well, EK is equal to 1/2 mv at point C squared. And the only value we don't have in that equation is the v. And we can isolate for v. And what you'll get is Vc is equal to EK times 2 over m, all square rooted. And you just plug in your values, and you'll find out what the velocity is at point C. Now, we've done it for one point. You can do it for all the points on the roller coaster. And if you want to, you have the values, you can go through. Do it with a friend. See if you get the answers the same as your friend. You can figure out what the velocity is at every point on this roller coaster.